by Manuel Schlund, talking about constraining uncertainties in climate sensitivity and gross primary production. Please, Manuel.
Yeah, thank you, Victor. Good morning, everyone. So I'm gonna be presenting our work on constraining uncertainties in multimodal climate projections with observations we did at DLR. And just a brief little motivation, you probably all know the increased effective climate sensitivity in the CMIP6 models. One second. You see here on the right-hand side, which is considerably higher than the assessed range from the different assessments report here illustrated with these blue bars. And similarly, the global warming projections of the different SSP scenarios show a similar high range in the CMIP6 models, as you can see here. And in this talk, I will present two different studies. So the first one will be about constraining the effective climate sensitivity with already published emergent constraints in CMIP6. And the second one will present an alternative approach using a machine learning algorithm. So let's get started with the first talk. The first paper, which is about emergent constraints on ECS in CMIP5. Do they hold for CMIP6? And here is an example of a published emergent constraint by Sherwood et al. From 2014, which uses the lower tropospheric mixing index, the LTMI, as a predictor for the ECS. And the physical mechanism behind this is that this tropospheric mixing is believed to increase in a warming climate, and the increase of this mixing rate will decrease the cloud amount in the boundary layer, which will then in turn increase the climate sensitivity and then increase the ECS. And since this is a positive feedback, we expect a positive relation between the LTMI and the ECS, which we find for the CMIP5 ensemble here in blue and also for the CMIP6 ensemble in orange. However, if we have a look at the coefficient of determination, R squared, and the statistical significance illustrated with this p-value here, we find that in the CMIP6 ensemble, we find a lower R squared value and a higher p-value, which corresponds to a lower statistical significance. Similarly, if we have a look at this probability density, which we get from the emergent constraints, so basically the y-axis here, we find that for the CMIP5 ensemble, the constraint range is lower. So here in this case, the standard deviation of 0.65 Kelvin, whereas in the CMIP6 ensemble, we get a standard deviation of 1.06 Kelvin. So the constraint is also weaker. And in total, we evaluated 11 different already published emergent constraints on ECS, ranging from 2008 to 2018. And for the sake of time, I will not go through all of them, but most of them are related to cloud processes and cloud feedbacks. And here's a summary of our evaluation. So on the left-hand side, you can see the different emergent constraints, the 11 we analyzed. On the x-axis, you find the ECS. And these bars here illustrate the probability densities I showed on the first plot. And the length of this bar corresponds to the uncertainty range. And the little vertical line here, the black line, corresponds to the best estimate. And we find that for all but one constraint, the best estimate of ECS is higher in CMIP6. That means this black line here is shifted to the right for the CMIP6 models in orange here. And also the range of this ECS, so the length of this bar is wider in CMIP6 for also all but one constraint. If we have a look at the coefficient of determinations, R squared here, we also find that this is higher in the CMIP5 ensemble than in the CMIP6 ensemble, which is not shown in this plot. So in summary, we find higher best estimates in ranges of the constraints ECS in CMIP6, which we think is likely related to higher multi-model mean and spread of the ECS in CMIP6. And as a possible reason for this reduced skill of the emergent constraints, when applied to the CMIP6, we identify that a basic assumption for these single process immersion constraints is that one single observable process dominates the uncertainty in ECS, which might not hold anymore for the more complex CMIP6 models. So for the second part of this talk, I will present our second paper, which is about the constraining uncertainty in projected GPP with machine learning. And the basis for this approach is the so-called multiple diagnostic ensemble regression method, the MDER, which basically uses multiple process-oriented diagnostics to constrain multi-model projections of Y. So these process-oriented diagnostics are shown here on the x-axis, x1, x2, and x3. And by using a multivariate linear regression, we tried, or the aim is to find a constraint for the target variable Y with a multivariate linear regression. So this is mathematically similar to the immersion constraints approach, but uses a multivariate regression instead of a univariate one. And in our approach now, we extend this idea and use a supervised machine learning approach to learn nonlinear relationships from gridded data. So the approach is illustrated here. We see two predictors, x1 and x2, but could be, of course, a higher number or a lower number, which are related to a target variable here on the z-axis. And all the different points here illustrate the different grid points of the different climate models. So the different climate models are color-coded. That means every blue point corresponds to climate model 1 here, and every red point corresponds to climate model 2. And the aim of this step is now to learn this this relationship, which is illustrated here with these with this gray surface using a machine learning regression algorithm. And to get more into more details, our aim is to constrain the change in the future gross primary production. So this is the target variable. And as the different predictors, we use temperature, precipitation, leaf area index, incoming radiation, and GPP of the historical climate. And in this first step, the aim is to learn this relationship between the predictor variables and the target variables using this machine learning model. In the second phase of our approach, call it prediction phase, we use observation-driven data of these predictors, of these 5 different predictors, and insert them into the machine learning model in order to get a machine learning-based prediction of the target variable. And here you can see the results. So on the left-hand side, you see the unweighted CMIP5 model mean, and on the right-hand side, the machine learning-based constraint projection of the global distribution of GPP at the end of the 21st century. And while both distributions look fairly similar, we also see that the colors for the machine learning constraint projections are lighter. That means we have a lower global mean.
2 minutes.
Thanks. Similarly, we find a reduction of the root mean square error for the machine learning approach in a perfect model approach of about 48%. To further evaluate the machine learning approach, we can have a look at this feature importances graphs. So on the left-hand side, you can see the global feature importances where we identify temperature, leaf area index, and historical GPP as the most dominant predictors. And on the right-hand side, you can see this importance of these 3 dominant predictors on a local level, where these blue colors correspond to regions where temperature is the most important predictor, for example, in the tropics here. And for example, the magenta colors correspond to regions where the leaf area index is the most important feature, which we find in the high latitudes. So as a summary, we find that machine learning-based approaches can reduce uncertainties in the gridded climate projections with multiple predictors, and the evaluation of the feature importance allows us to explore more of this process-oriented relations between the predictors and the target variable. So as a brief summary for this talk, in the first part, we found that emergent constraints on ECS show a reduced skill and increased best estimates of the effective climate sensitivity in CMIP6. And in the second paper, we find that machine learning techniques are promising methods to improve the analysis of Earth system models. Thanks very much.
Thank you very much, Manuel, for a nice summary of your work. And there is first question from Colin. Does the larger spread of emergent constraints on equilibrium climate sensitivity in CMIP 6 compared to CMIP 5 suggest a problem with a constraint, or just that CMIP 6 models are more variable and thus don't reproduce the emergent or Earth system model as well?
So we couldn't identify one single reason for this. So one possibility is that, of course, the emergent constraints were just appeared by chance in the first place. So when they were identified in the CMIP 3 or CMIP 5 ensemble, and which would, of course, explain why they didn't work in the CMIP 6 ensemble. But since since all of them are based on explainable, robust physical mechanisms, or at least we think that they are robust, we think that a more likely reason is that the increased complexity in the CMIP 6 ensemble didn't allow us to use one single observable process anymore to constrain ECS. And we think that therefore we should focus on multivariate approaches.
Mm-hmm. Next question is from Ruth, and this is about whether you tested other machine learning methods and do they work?
For ECS or for?
I guess this was for GPP.
So we tested different algorithms. So in this case, we used the so-called gradient boosted regression tree algorithm, but we didn't find any large differences between the different algorithms. But if you think of different approaches on how to implement the weighting, no, we didn't.
Yeah, next question is from Reto. Is there a danger that the constraints are overconfident because many of or all models use very similar and potentially biased parameterization of GPP?
Or can you repeat this question? Or
so is there a danger that constraints are overconfident because model use the similar parameterizations?
Yes, so of course we rely on the different climate models. So if there's like structural errors in there, it might of course be that our approach is overconfident. Yes, but we applied these different tests and different evaluations and hope that we could tackle those problems. But yes, we are.
Yeah. Last question from Chris Johnson. This is whether emergent constraints get applied to ensembles or just one realization.
So on the first start, yes, we only used one realization for these emergent constraints.
And would you learn more if you just use a large ensemble comparing to one realization?
We tried in the very beginning to use like ensemble means for different realizations for one climate models, but we didn't find the results didn't differ much. So we decided on using just a single ensemble member.
Yeah, thank you very much, Manuel. And we move to the next talk, which will be by Franco Catalano, who will tell us about land surface feedbacks on temperature and precipitation, and also results from LS3 MIP.
Yeah, thanks. Let me share the screen.
Yeah.
Okay. Sorry.
Not yet in the full mode.
Yeah, let me just, okay.
Still not in the full mode.
Okay, now I should be.
Mm-hmm.
Okay, so good morning. I'll present the first results on the land surface feedbacks on temperature and precipitation in the CMIP 6 LS3 projections. So this is a work done in collaborations with other people here from other center, Andrea Alessandri, Wilhelm, and Thomas Herring. So what is the aim of the LS3 MIP experiment? Is we have to assess the role of the land atmosphere feedbacks on climate change and isolate the impacts of the soil moisture changes on temperature and precipitation climate change. So I'll first briefly describe the experiments set up, and then I'll go through the results obtained in the Easy Earth community, and then I'll show the results with the full multimodal of the LS3MIP in CMIP.
Yeah, sorry, Franco, we still see non-full screen.
This is...
you share the screen. Can you perhaps swap the screens if you have two ones? So we see.
Let me just stop share the screen. Desktop share. Now?
Yeah, now it looks much better.
Oh, okay, perfect. Sorry for that. So this is the LS3MIP, LF-MIP experiment setup. The LF-MIP is the land feedback MIP of the LS3MIP. So basically we have 4 experiments. The first couple of experiments we prescribe the climatological soil moisture from the historical CMIP-6 run. All these experiments are EMIP, so SST and CIs are prescribed from the fully coupled SSP 2.6 experiment in the F1, and SSP 8.5 experiment for F2. So the PDLC experiment is the one with prescribed climatological soil moisture, and the RMLC has prescribed 30 years projected soil moisture running mean from this scenario. So yeah, in the first idea was to perform a couple of experiments, but then in the LS3MIP community we decided to switch to EMIP because of some problems with the ocean coupling, especially due to the runoff. So all the experiments are EMIP. We performed all the Tier 1 Easy Earth LF-MIP experiments at ENEA, and all the data are now published on the ESGF node. So let's go through with the Easy Earth experiments first. So here we see the climate sensitivity, which is the difference between the RMLC and PDLC experiments. These are the climate sensitivity in the differences of the 2071, 2100 minus 1985, 2014 periods. So the first line of the two maps here show the soil moisture sensitivity. So we see that in both scenarios we have an increased soil moisture, so which is a wetting over some boreal forests and over the Sahel and in India. And we have a drying signal over Europe, which is much stronger in the SSP 5.8.5 scenario, over the US and in South Africa and Brazil. And this signal in the soil moisture corresponds to a reduction of the latent over the regions where we have a drying, and an increase of the latent where we have moistening signal, and the opposite signal for the sensible heat, which is the bottom two maps. And of course, the signal is much stronger in the SSP 5.8.5 scenario. Let's see what happens with the temperature. So we see that in both scenarios we have a warming signal. This is the upper two maps. And on the bottom maps, we see this sensitivity. So basically how the soil moisture contributes to the warming. And we see that the soil moisture contributes to warming, especially in the regions where we have a drying signal, so before, but we also have counteracting effect, especially over the Indian monsoon region and over the Sahel, where we have a reduction of the temperature due to soil moisture forcing. Well, let's see what happens with precipitation. We see generally in the upper two maps, for both scenarios, an intensification of the hydrological cycle, mostly over all the globe, apart from some southern Europe and some parts of the southern hemisphere. And in the lower two maps, we see how over the regions where we have a drying signal, again, it contributes to a further reduction of precipitation. And here we see an interesting difference between the two scenarios over the Indian region, where we have an intensification of precipitation in the SSP 5.8.5 scenario, which is not clear in the stronger mitigation scenario. Okay. Interestingly, here the signal over the Sahel is somehow contrasting, so we have a reduction of precipitation due to soil moisture forcing, and this can be mostly related probably to some changes in the dynamics which have to further examine. So let's see what are the 5 different Earth systems models contributing to the LF-MIP multi-model. We have Easy Earth, the results presented so far. Then we have Anchor, CSM2, the PSL model, the MPI model, and the CNRM model. The model differs by the land surface model and also for the resolution, although the resolution doesn't seem to be very important parameter here for these considerations. So let's see what happens. Again, these are the soil moisture latent and sensible fluxes. We see that results are mostly consistent with what we already saw with the Easy Earth model. And so we have a strong drying signal over Europe. And again, the signal of moistening signal over the Sahel is still present, especially for the 8.5 scenario. And the response of the latent and sensible heat fluxes are still consistent. Although the signal here is much, I mean, the differences between the two scenarios are stronger than with the easier model alone. So this is for the temperature. Again, we see a clear signal of intensification of warming due to soil moisture forcing, especially in the SSP 5.8.5 scenario. And the same with the Sahel. Here, the two scenarios are quite consistent in the moistening signal over the monsoon region and the Sahel. And okay, so let's see finally the precipitation.
2 minutes.
For the multimodal. Yeah, thanks. So here we see again intensification of the hydrological cycle, but here it is more clear the signal, the contrasting signal of a reduction of precipitation in the 21st century change over the Europe. And but we see that again clearly the sensitivity to soil moisture is to further reduce precipitation, especially over Europe and also over the West Europe and East Russia, and over the United States. Again, we see this signal over the Sahel with 2 different bands, one with increased precipitation and one with the reduced precipitation. And this is clear. I mean, this have to be further examined, and then the intensification over the Indian region, which is actually different to what we see in the stronger mitigation scenario, where we see a reduction over the Indian region. Let's go to conclusions. So these are the first results of the land surface feedbacks on temperature and precipitation. And we see that Easy Earth results are overall consistent with the full LF-MIP and MIP. See the temperature change is positive everywhere over land, and the climate change signal of precipitation is mostly showing an intensification of the hydrological cycle, especially in the northern hemisphere. Over the regions where we have a negative soil moisture change, the temperature increased significantly, while cooling signal is not so significant overall, the regions getting wetter. And the larger effect of precipitation to soil moisture forcing occur over transition zones between dry and wet climates, like the Sahel, for example, where evapotranspiration is highly sensitive to the soil moisture. And of course, the sensitivity of both temperature and precipitation is much stronger in the 8.5 scenario. So this is all from my side, and I'm happy to take questions.
Thank you very much, Franco. So there is no yet questions in the chat. So my first question is, did you get some surprises in this experiment, or was it what you have expected?
Well, mostly results are consistent with the Glasse CMIP-5 experiments. But we are also seeing some important differences, especially in the Sahel regions, where we didn't see in the Glasse CMIP-5 a strong contracting effect on temperature due to soil moisture and weather. Here we see quite an important signal there. But yeah, for the northern latitudes, especially in Europe and North America, the signal is quite consistent. And this is also due to the fact that the setup is very similar, because we are still using an EMIP setup. So of course, yeah, we expect.
Thank you, Franco. There is a question from Ruth, which is, I think it's very similar. Have you looked at the differences between models in your 5 model ensemble, and are all consistent? And she asked because of in the old Glasse CMIP-5 run, some of the difference between models were very large, but you would not necessarily see it in the
Yes. We of course we are looking at the differences among the models, and we do see some important differences. And of course, because also the initialization is quite different. I mean, the prescription of the soil moisture is not, I mean, there are some differences in although all the models are adhere to the protocol, but for example, not all the models prescribe the full liquid content. Some prescribed all liquid and ice content of water. So there are some differences, but
thank you. Thank you, Franco. I think for the sake of time, we move forward. You can also answer Ruth's questions in the chat. And now we move to the next talk by Øyvind Seland. Øyvind, can you share your screen?
Yep, I'm going to try to share it. Let's see. You see it?
Yes, excellent. So
yeah, assessing climate states and feedback in 2 versions of NORSM2. A number of co-authors who are included figures or numbers from. An overview is just going to go through the 2 resolutions we're talking about, and tuning a bit on tuning targets. Selected fields for comparison measurements, that basically temperature, precipitation, and sea ice, which are selected, since there's an infinite amount of fields that you can look in the climate model. Climate sensitivity, and just an example of a response to scenarios for the 2 versions. Yeah, don't skip that one. NORSM2 version, it's not very high resolution, but it's one on nominal 2 degree and nominal 1 degree in atmosphere, and 1 degree in ocean. Although the physics are quite complex, so the models tends to be quite expensive, in 1500 CPU hours per model year, even for the 2 degree version. So saving time, particularly if we want to be involved in many MIPs, is crucial. So at least, whether it's on purpose or not, at least we try to keep the models quite close from the first place. So we initialize from the same ocean state, and we tune them sort of in tandem, and had a goal of getting similar ocean volume temperature and comparable cloud forcings although mainly from a manual point of view and not machine learning way of doing it. And a comparable length of spin up. Going to the bias from the historical period, the 2 degree is slightly warmer than the 1 degree. You see that so the bias in this case is smaller for MM, that's mainly a question about being a colder model. RMSE is also better in the high resolution one. The difference is mostly connected to the extratropicals. The difference is less smaller over the equatorial regions. And this cold bias that you see in the 1 degree version in the northern hemisphere can also be found as an when you look into the sea ice. The southern hemisphere now is you can see the ensemble spread in the model, and also for that matter the spread in the observations. But the main difference is the 2 degree in northern hemisphere summer, where the cold, relatively cold 1 degree has too much sea ice, while 2 degree versions follows the observation quite close. Precipitation, again, actually the biases are very similar, although the RMSE for the final resolution version is much better. And you see, in particular, over part of the western continents, like in South America, and also out into the ENSO regions, the biases is reduced in the final resolution version. Not going to much detail, but I mean, after all, it's aerosols that we work a lot on, and basically the AOD comparison measurements, 2 degree on the left, 1 degree on the right, basically the bias and R is very similar. You can see there's a tendency to have some very high model AOD numbers, which is connected to a tuning that you need to employ in which we increase the sea salt. So the sea salt, amount of sea salt, or in particular the amount of sea salt AOD is a bit too large. There's a minus for the also, since the aerosols I included the ARFs here. It should be a minus, of course, in the 2 degree. But still, minus 1.36 and minus 1.26 is not too different, in particular if it also would take into account ensembles in which basically this number comes with a plus minus 0.05. Climate response. As Ada showed yesterday, it's not really a long-term ECS, but a standard way of doing effective ECS. And those for the ECS that are very similar. TCR, there's some difference, although so the 2 degrees being a bit more sensitive. TCRE and the carbon cycle basically follows the TCR. And the similarity in ECS can also be seen all the way in the different radiative feedbacks, which is a slight difference in water vapor feedbacks is perhaps the main difference. Not even the cloud feedbacks are very different. This is a temperature trend from all the ensemble members scaled so that it's a bias, so you don't see the difference between scaled towards the not the bias, but 1850 to 1880 values. So the bias is removed, and as number of other models is a bit too much cooling in the 60s, 70s, and then a warming again, which is more comparable to observed warming. And again, the variability inside ensembles is much larger than the difference between the resolutions. at the end is just, guess you can also mention that even if you include the number of, we have parameters, then these three I was talking about, you still see much of the same story, that usually you're getting slightly better, but very similar results for the two model versions. And finally, at the end, some scenarios. 2 meters, again, 2 degrees on the left. And the difference is almost, you see, the patterns are almost identical for the temperature responses. You can always look into some small differences here and there, but I don't think they are significant. Ice, here you see the one major problem with the final resolution, which the warmer 2 degree has a much better representation of also the reduction period of sea ice. For SSP 37, though, the ice summarized, Northern Hemisphere summarized has gone towards the end of the period for both resolutions.
2 minutes.
Yeah, changing the precipitation rate. Again, the increase is almost the same, although that's you can find some. There seem to be some circulation pattern going on in the tropical Pacific, but in general, you find most of the same patterns for both model versions. Which is sort of, I'm not whether we hope to find it out, I'm not certain, since we always would like to have final resolution, but at least they seem to be very similar. So, climate responsive feedbacks, quite similar for both resolutions. Overall bias, similar, but usually better spatial patterns. Too slow melt in the 1 degree version due to the initial state, or basically article bias. And then of course the question whether these are valid also for high resolution, since they're known to be changing in improvements. 150 is typically better extratropical and blocking, and 50 to 25 you get a better tropical cyclone and large scale treatment of monsoon systems. Yeah, that's thank you for the attention.
Thank you very much, Øyvind, for your nice presentation. There is a question of Colin on aerosol, radiative forcing of aerosols, yeah. And whether the forcing was very negative, and let's explain the historical cooling.
Yes, just trying to lost the view here.
No, we don't see.
I'm going to stop here. Then it's fine. Yeah.
Yeah. So, was it aerosol mostly responsible for this historical cooling, which you showed in your slide?
Yes, probably. Although since we have a relatively low ECS, that kind of the low ECS won't get the cooling, but of course a combination of the low ECS and a relatively low TCR, and not very. There's many models having more cooling aerosols, but so a combination is probably involved here as well, not only the aerosols.
Yeah, and then was Colin comment that increasing ocean resolution may be more computationally efficient and give better results? Just.
Possibly, and it's so we actually considered having a higher ocean resolution, but that's so we've been experimenting with quarter and actually also 1/8 degree ocean resolutions, but we also have biogeochemistry, so that actually makes the increasing the ocean resolution actually increases also a bit more cost than only a physical ocean.
Yeah, that's clear. Okay, thank you very much, Øyvind, again. And we move to the next talk by Ruth Lorenz, and she will tell us about comparison of CMIP generations in terms of temperature and pressure.
Thanks, Victor. Yeah, my name is Ruth Lorenz. I work at ETH, and this is a presentation of mainly results we compiled for CRESCENDO, and it's done together with Anna Mary Field, Lucas Brunner, and Reto Knutti. And Oops. Sure. So a bit of motivation. We've already seen these graphs. So with every new generation of more complex climate models, which run scenarios to be used, for instance, in IPCC, there's the expectation that they provide more detailed and also more certain projections. But the question is this really the case? For instance, here we see the global mean temperature for CMIP5 for different scenarios, and then the same for CMIP6, and this is from Tibaldi et al. In 2021, so very recent. And you can see that the spread here in the models for a high emission scenario, for instance, is increased versus CMIP5, so the uncertainty actually didn't decrease in this case. We probably wouldn't expect these graphs to be identical, given that the scenarios are different, but still I think lots of people were a bit surprised by how big this difference was. And we've already seen over the last few days multiple reasons why this might be the case. But yeah, these are the kind of questions we try to tackle in the group. So for instance, how to make the best use of the climate model projections we have. Does weighting multi-model ensembles improve our understanding of uncertainties? And very recently, we started to look into how the robustness and uncertainty change from CMIP3 over CMIP5 to CMIP6. I've mentioned model weighting, and this for CRESCENDO, a large part of work we did was on model weighting. So why do we need to weight climate model projection ensembles? Two main issues. The first is some models are better than others. This is illustrated here on the Arctic September sea ice extent over time, and you can clearly see that black is the observations and in colors are the different CMIP5 models. And you can see that some models start off with less sea ice than were measured, and others still have more sea ice by the end of the 21st century than were measured. So the multi-model mean is probably not your best choice if you try to project when the Arctic will be ice-free. I mean, we've done model evaluation for a long time, but very often this then still isn't really incorporated into the assessment of multi-model projections. The second issue is that models are not independent. This is illustrated here in something we call a model family tree. It's mainly based, or it's basically based on only output of the models. The only information on what goes into the models is kind of the coloring we use here. So yeah, so it's a statistical hierarchical clustering on the generalized. So you've got the generalized distance here, and it's based on like temperature and precipitation, for instance. And you see that closely related models like 2 easy Earth versions here, they cluster together, but you also obtain some larger model families where it might not be totally obvious from just the model name that two models would be very similar. So how can we weight climate model projection ensembles? There are lots of different methods around. Performance-based methods, Bayesian methods, detection attribution-based methods, and we've already seen some results from Manuel this morning on machine learning methods. They all have a common goal, and it's what I call here an expertly vetted uncertainty. So you want to incorporate model evaluation into multi-model assessments. So you use the emergent relationships which link the present behavior to future changes and end up with a more meaningful ensemble. The equation we normally use in the group here is the one depicted down here. So you've got a weight WI for each of your model. It's basically two terms. One term increases the weight if the distance to the observations is small, and the second one decreases the weight if a model is similar to others. And we've used the method, for instance, on the September sea ice case shown here. The unweighted multi-model mean is here in black, and the gray envelope is the unweighted spread, and then the red would be the weighted multi-model mean with a decreased spread if you weight. And you see the red line moves a little bit closer to the blue line, which is the observations. But we've also found it doesn't overlay the observations completely, because we're not only basing this on the sea ice trend, but only on other variables like temperature, seasonal cycles, etc. And an important thing we found within CRESCENDO was that the weighting really needs to be based on multiple diagnostics, and this is shown here. This is one example using different observational data sets where you can see this very clearly. So depending on the number of diagnostics you include to inform the weighting, if you only use one, you might end up with a very different change in the mean depending on which observational data set you use. And this kind of goes a bit away if you use more diagnostics. It's also shown on this graph over here to the right, where you have the improvement, which is relative to the unweighted in percent here. And the darker colors mean that you included more diagnostics into your weighting. You can see that your chance of having a better weighted mean increases if you use a higher number of diagnostics. You can also see that the period length you might use to inform your weighting also helps to improve your skill. The period length for the performance, for instance, this might be limited by observational data availability, but for the independence, for instance, you don't really need observations, so you can you benefit if you use longer periods. And we were also able to show that by using single model initial collision large ensembles, that it helps if you use some large scale predictors for the independence. We've used the weighting to weight global temperature projections from CMIP6, and this is shown here. We've only used temperature and surface pressure, but for the independence, we used climatology of these two variables, and for the performance, we used trends as well as anomaly and variance-based diagnostics. And the outcome is shown here. So we've got the temperature change relative to a base period for two different time periods, one kind of near future and one at the end of the 21st century. The gray is the unweighted, and the colors, the blue one is a low emission scenario, the weighted, and the orange is a high emission scenario weighted. And what you can see is that you decrease the uncertainty or the spread mainly at the top, especially here at the end of the century for the SSB 585. And this is due to some of these very high warming models which obtain less weight. Now, I said I'm also going to say something about robustness. How do we measure robustness? So we use a measure that's inspired by the signal to variability ratio in a rank probability skill score, and it's been introduced by Knuti and Sedlacek in 2013. It does include the magnitude of the change, the sign of the change, natural variability, as well as intermodal spread. Most importantly, if R equals 1, you have a perfect model agreement. So a higher model spread or smaller signal would then decrease R. If R is similar or approximately 0, the model spread is comparable to the signal. And if R is smaller than 0, then the spread is much larger than the signal. And we visualize it like this, shown over here to the right. So if R is larger than 0.8, you have small dots on a map. And if it's larger than 0.95, you've got large dots. And we also included a measure of statistical significance for the mean change. And if less than 80% of the models have a statistically significant mean change, there is hatching. Then you've got a special case over here where you have hatching. So no statistical significant mean change, but still a high robustness. And this basically means that you have an agreement on a change in shape.
2 minutes.
Thanks. So I'm going to mostly skip over this. This is basically how you calculate R. You need these two areas. One is just based on the signal here, so from historical to projection, and you use some CDF, so some cumulative density functions. And the second area, A1, is based on the multi-model mean in the future, but then also the individual models, which kind of create the CDF, and then you calculate R like this. Some results. So this is for precipitation for CMIP6, CMIP5, and CMIP3, two different time periods, a near future and a far future. You can see for the near future, there's lots of hatching, so no really significant change in the mean, but still there is some stippling, so some agreement on the change in shape. For precipitation, clearly less hatching and more robust changes. But given that on these maps, it's really difficult to compare the three different generations, I'm also going to show it to you in this way. So here you have the percentage of Earth's surface with R larger than 0.8 on this axis, global mean warming on this axis. So this is to get rid of the differences in the scenarios. You can clearly see that with larger warming, the robustness increases. This is true for all generations, but you also have a clear increase from CMIP3 to CMIP5, and then a further increase in robustness towards CMIP6. The gray crosses here are results from large condition ensembles. So that means that this is kind of the maximum of robustness you could obtain due to internal variability. And given that I talked about weighting at the beginning of my talk, you might wonder what happens if you actually weight these ensembles. I have to say that we only used one ensemble member per model for these estimates, and we also included only performance in the weighting.
10 minutes.
Yeah, fortunately, there's not really an improvement in the robustness if you weight. So I'll come to my conclusions. There's lots of evidence that the weight, given one weight for each available model projection, is suboptimal due to different model performance and lack of independence. Weighting is a more formal way to estimate uncertainties, which is consistent with past trends and mean climate. The robustness, as we define it here, increases over CMIP generations, but the overall global model agreement on mean precipitation does not improve by defining global weights. Thank you.
Yeah, thank you, Ruth. So one question from Herr Schulz. What exactly penalizes the high equilibrium climate sensitivity model in the weighting procedure?
That their temperature trend isn't represented very well in the historical. That's the main reason why they're downweighted in this case.
All right, and Øyvind also have a short question. Sometimes observations are also related to different observation products. Do you also weight observations by closeness?
No, we don't, and we have thought about it, and it's true that this might be the case so far. Like very often we use maybe up to 3 observational data sets, and we've changed from kind of using like just do the same thing for different observational data sets to kind of using a median of the observational data sets or using the maximum distance to the observational data sets. Yeah, but you're right that you might need to also weight the observational data sets if you do these kind of things.
Yeah, thank you very much, Ruth. And for the sake of time, we move to the last presentation, which will be from Tuula Aalto, from Finnish Meteorological Institute, and also about methane emissions again. But I understand, Tuula, this time It will be about GSBach, right?
Comparison of different models.
Comparison of different models. Yeah, not yet full screen. Now yes. Full screen. Yes.
Yes.
Please.
Okay. Sorry. Oh, sorry.
All fine.
Like this. Yes. So I will talk about methane emissions in Northern Europe. And in Northern Europe, we studied the region of Fennoscandia, which is rich in wetlands, and the large variation in precipitation and temperature induces significant variation in the regional methane emissions then. And here we compared the temperature and precipitation responses of CRESCENDO model methane emissions to global carbon project models, atmospheric inversions, and also upscaled flux observations. And here in the first figure, you can see the methane emissions plotted against precipitation and temperature. And the CRESCENDO models, JULES, CLM5, LPJ GESS, GSBach-Himmeli, they show high emissions in the high temperature range, while, for example, the LPX burn shows high emissions in the high precipitation range. And also there are on the global carbon project diagnostic model ensemble mean and the prognostic model ensemble mean. Diagnostic is the one where the wetland extent was prescribed. And in here, the emissions are more spread around the range, but still they are like the highest emissions come in the high precipitation temperature range. So the more spread you can expect when you have a model ensemble. And in the next figure, for comparison, we also checked how the coupled model runs look like. We took data from the CMIP 6 inventory, and there we noticed that both the uncoupled models and the coupled runs, they showed pretty similar responses to temperature and precipitation. And then we looked at the seasonal cycles, and there both the magnitude and the maximum of the annual cycle varied a lot among the models. And if we first look at the global carbon project diagnostic mean and the prognostic mean, as well as the global carbon project prior for the inversions, and also the posterior from global carbon project inversions, they show that the maximum would be around August, and that is also true for the upscaled EDIFLUX product, while then the individual models show more variation in the maximum month of emissions, ranging from June to September. And to summarize at this point, the high emissions were correlated with high temperature in joules, LPJS, JS/Himmeli and CLM5, and high precipitation in LPX-Bern. And the annual maximum was most often in July or August, but varied from May to September. Then what we did next, we studied the models as priors for atmospheric inversions. So we studied how the information from the atmospheric concentrations would change the responses. And there we used models with contrasting temperature and precipitation responses, the LPX-Bern and JS/Himmeli, as well as the global carbon project prior, as prior for the atmospheric inversions that were performed with Carbon Tracker Europe methane. And when you look at the posterior, you cannot see so much, but when you look at the lowest row there, the posterior fluxes divided by the prior fluxes, there you can see that the inversion wishes to put the higher emissions in the high temperature range in LPX-Bern. So it wishes to change the responses of LPX-Bern to more temperature limited direction, so to say. And in JS/Himmeli, it's vice versa. So it wants to increase emissions in the high precipitation range. So move the JS/Himmeli responses to more precipitation limited direction. Whereas when you look at the global carbon project posterior, then there the increases are suggested more evenly in the ranges. So there is not so much wish from the inversion to change the temperature or precipitation responses. Okay, and this is also seen when we look at the seasonal cycles. So when looking at the GCP prior and posterior in the green shades, the month of maximum emissions is not changed. But when we look at the JS/Bach, then the inversion changes the month of maximum emissions to August, when it was first in July. And in LPX-Bern, it was first in September, October, but the inversion changes it to July, September. So to conclude, the ecosystem model methane emissions were either temperature driven or precipitation driven, and the inversions attempted to move the strongest responses towards co-limitation. And the shape and the maximum month of the annual emission cycle varied among ecosystem models, while inversions, GCP model ensembles, and upscaled flux observations suggested July-August as maximum. And then the reasons why, for example, LPX and JS-Bach differed from each other so much is on the emission component for peatlands and for the wet mineral lands. So the peatland component is very large in JS-Bach and has a strong temperature dependence, and thus the maximum emissions occur in July, while in the LPX, the wet mineral land component is comparable to the peatland component, and the mineral land component has maximum later in the autumn, and it's also, as you could imagine, it's more precipitation dependent. So these are like component-wise the reasons, but in reality we should go through a more specific checklist on where these differences arise from, and also look at the reasoning for the other models, as they really do differ in their predictions of soil moisture, water table levels, wetland area, peatland maps. How do you use all this information here, and soil carbon component, respiration, vegetation types, phenology, and also the processes for methane formation and those temperature dependencies. Okay.
Thank you very much, Tuula, for your presentations, also for staying in time. And we have just one question from Thomas, whether GCP precipitation has a low bias or underestimated in the high latitudes. Do you know that?
Let's see if I can. So it has, GCP has, if it has a bias in the precipitation, I don't know. I'm not sure whether it doesn't show like really like that from our results really strongly that it would have, but I don't know if there are people who have better knowledge on this.
Okay, so we can discuss that offline with forcing. I also have one question, and that's on what really defines the seasonal course of methane emissions. Is it climatology, or is it also productivity, which comes from the model, like JS-Bach or joules?
Yeah, it's both. I would say, well, the process descriptions in JS-Bach Himmeli, for example, here, how we used it, they played a role, and the strong temperature dependencies. But as I mentioned, the LPX burn was a bit different, and their soil moisture plays a big role. And then how do you model the soil moisture, and where do you have the dependencies there? That's more complicated, maybe. Okay.
Yeah. Thank you very much, Tuula, and I also want to thank all speakers of this morning session. And whereas you still can pose some questions in the chat, and we reconvene in about 1 hour, and Ruth Lorenz will chair the next session. So thank you very much. And Tuula, you can stop sharing your screen. Yeah, excellent.
Thank you, Victor.
Thank you.